Okay, so the plan for today is just to really pick up where we left off last time with graphing and continue with it. We might finish it up today. We might finish it up next time. The quote of the day, there's kind of two quotes that are, I think, kind of related to one another. One is by the philosopher Friedrich Nietzsche, from his book Beyond Good and Evil, where he has kind of a section of like little aphorisms or quotes or short sayings. And this is a pretty famous one, maybe one of his more famous quotes. Whoever fights monsters should see to it that in the process he does not become a monster. If you gaze long enough into the abyss will gaze back into you. So kind of a cool, saying. There's several different ways it's been translated. He wrote in German originally, so different translations have a slightly different tone to them. But I think the at least one of the things that's coming across is that sometimes you decide, to fight against something and for a moral or a principled reason. And then the fight becomes the principled reason, and you kind of lose track of the original reason that you were fighting against it, right? Or I think, a similar, similar sentiment maybe in the Silmarillion, um, the book that kind of built the world. It's kind of the world building book for Middle Earth, for Lord of the Rings and The Hobbit. So it's like kind of the history of Middle Earth, basically. Um, and there's a quote in there: "For those who will defend authority against rebellion must not themselves rebel." So I think it's a similar type of idea. So I thought just a couple related and interesting quotes for today's class. All right, so jumping back into graphing. Recall the strategy for graphing functions. We basically kind of work our way up the ladder of difficulty or complexity. We start by doing the basic algebra first, doing, finding intercepts, points of interest, analyzing symmetry. Is the function even or odd? What's the domain or range, things like that. Then moving on to what we might call something like pre-calculus, finding asymptotes in end behavior. Are there any vertical asymptotes? What about horizontal asymptotes or end behavior? Moving to our first derivative, looking for, and by the way, usually 1 and 2 can get you some anchor points and some end behavior, so you kind of know maybe what some of the intercepts look like and what the end behavior looks like, but you usually don't know what the middle looks like, right? So that's what we're trying to kind of clarify in the next couple of steps, is filling in a little more of that detail. 3 and 4 deal with the first derivative, finding the intervals of increase and decrease, and then the locations of all of the local extrema. And then fifth, basically doing the same thing with the second derivative, finding intervals of concavity where we're concave up versus concave down, and inflection points where we change concavity. And as I note here, some of these can be very difficult to do. Sometimes taking the second derivative for a function is quite cumbersome. Sometimes finding y-intercepts is usually easy, but finding an x-intercept might be quite difficult for some problems. So we want to look at the individual problem and think of these as tools in a toolbox, and we can, assemble them. Maybe, if we recognize that, say, maybe finding an x-intercept is difficult but not impossible, maybe we do the rest of our process. And if we need to, we can come back and find the x-intercept if we really need to, but we might have enough information from everything else that we don't need to find that, right? Or maybe we have enough information that we don't feel that we need to take the second derivative and evaluate intervals of concavity. Maybe we feel that we're good with just steps 1 through 4, and maybe it's quite cumbersome to take the second derivative, but we are happy with what we have at that point. So, yeah, so we want to strategize based on the individual problem. I want to start off with an example that we did last time, and this builds into this next example. So we're going to do this one again as kind of a warm-up, and it's going to build into the more general example, which is really starting to get at the crux of why we're doing this. One big question is, why are we doing this by hand if we can just plug the function into a calculator and have it graph it for us? Well, something like this, we certainly could do that. But something like this is a family of functions. We have f of x is some function that involves parameters mu and sigma. if I want to understand, so for a given choice of mu and sigma, I get a certain function, and for a different choice of mu and sigma, I get a different function, right? So I have kind of a function of x, but that's dependent on these parameters mu and sigma. They're almost a little bit like variables themselves. If I want to understand how, changing mu changes the characteristic of the graph, or, what does mu do to this graph? What impact does it have? And the same with sigma. I might want to understand the family of functions more generally, not just picking a couple choices for mu and a couple choices for sigma and getting different graphs. And, they're all going to look kind of the same. So if I want to understand what mu does or what sigma does, going through this by hand is really going to be an important thing to do. So that's really, kind of the thrust of this section. Okay, so let's work back through this one. Again, it has been a few days, so doing a warm-up is not a bad idea. So we have f of x equals e to the negative x squared. And let's first look at x and y intercepts, symmetry, etc. Well, we see that f of 0 equals 1. So 0, 1. Well, 0, 1 is the y-intercept. We note that there is no x-intercept, and in fact, f is always positive. So we're in quadrants 1 and 2. And we also notice that the only place that x comes in is an x squared, so it's actually an even function. Just kind of from our basic algebra, we can already tell quite a lot about this function. So we have an anchor point. We know we're not going to be at quadrants 3 or 4. We have an anchor point, 0, 1. We're an even function, and we stay positive. Second, asymptotes and end behavior. Are there any vertical asymptotes? In other words, is there any like f of a equals plus or minus infinity? Kind of in quotes. And no, there's not going to be any vertical asymptotes here. So what about horizontal asymptotes or end behavior? What about the limits at infinity? So for vertical asymptotes, we're looking for the presence of infinite limits. For horizontal asymptotes, we're looking for limits at infinity. We know it's an even function, so whatever its limit is at positive infinity, it should be the same at negative infinity. So f at plus or minus infinity, well, e to the minus x squared is 1 over e to the power x squared. Put in a bigger positive or negative value for x. X squared is going to make it an even bigger positive value. E to that power is going to make it an even bigger still positive value. So bigger input yields a bigger output in the denominator. That drags that fraction down to 0. So we have a horizontal asymptote of y equals 0 at plus or minus infinity. And so again, we have a decent bit of information about our function already. We know it's got to have these horizontal asymptotes, but then the big question is this like a local max here or a local min? Does it do something like this? Right? Does it do something like this? Does it do something else? So that's what we want to clarify with steps 3 and 4, and then perhaps step 5. So if f of x is e to the negative x squared, f prime is e to the negative x squared times negative 2x. So for f prime, we see that if we set f prime equal to 0, x equals 0 is the only solution. So we have only one critical point. F is, of course, differentiable everywhere. I might also note that f prime is odd. F was even, so its derivative is odd. When we take derivatives, we switch the evenness to odd and vice versa. We switch that symmetry. And we remember that derivatives have this intermediate value property, or we could just observe that this is a continuous function. So I pick a test point, say maybe the number 1, that's in the interval 0 to infinity, see whether f prime is positive or negative there. And I see that when x is positive, negative 2x is negative. E to the negative x squared is positive. It's always positive. So f prime is negative on the interval from 0 to infinity. And either by the oddness of f or by, say, picking a different test point, -1 or something like that, we can see that f prime is positive on the interval negative infinity to 0. F prime being positive means f is increasing on negative infinity to 0, and f is decreasing on 0 to infinity because f prime is negative there. And lastly, we have a critical point, x equals 0, where we're increasing into it, decreasing out of it. F has a local max at 0, 1, at x equals 0, and the maximum value is 1. So we do see that we don't have any extra wiggles. We increase into here and then decrease out of there. And then we could evaluate the second derivative as well. So I have for the first derivative, I have the product of two functions of x. I'll think of this like negative 2x times e to the negative x squared. So differentiating the first gives me negative 2 e to the negative x squared. And then plus differentiating the second gives me an e to the negative x squared times another negative 2x that comes down and hits the first negative 2x. So that's a plus 4x squared. So that's f double prime. And I suppose I could clean this up a little bit. I can pull out a 2 e to the negative x squared. And then I get -1 plus 2x squared. Does that look good? Yeah, I think that looks good. So this is what f double prime is. And we can ask, when is this 0? Well, 2 e to the negative x squared is always positive. So that's when x squared is 1/2, or when x is plus or minus 1 over root 2. And then lastly, I'll pick a couple of test points, maybe say 0. F prime at 0, well, remember, this piece is always positive. So the sign of f double prime is just going to be the sign of this brackets there. And if I plug in x equals 0, that's a negative. So we're going to be concave down here. That does make sense with our picture too. We'd expect to be concave down. And 1 over root 2 is, say, between 0 and 1. So I could pick 1 that's to the right of that. So f double prime of 1, 2 times 1 is 2 minus 1, that's positive. Also, f double prime is an even function. The only place I see an x come in is as x squared, so it gets rid of all negatives. The f of negative x looks the same, or sorry, f double prime of negative x looks the same as f double prime of x. So the evenness tells me that I've got a nice symmetry here. The region to the right of 1 over root 2 has a positive second derivative, so the region to the left of -1 over root 2 has a positive second derivative as well. Or we are concave up on negative infinity to -1 over root 2 union 1 over root 2 to infinity and concave down. On that middle interval. And we have inflection points at plus or minus 1 over root 2. So that maybe helped us confirm a little bit that we were happy with this shape. And it also gave us these inflection points at negative 1 over root 2 and positive 1 over root 2. So if we wanted those inflection points, if we wanted their location, we would have to find the second derivative and go through that. Otherwise, this just acted to kind of confirm that the general shape that we had drawn before does seem to be right. Any questions on this one? Okay. So now let's take a look. Let me actually edit this so that it's there. If I put it on its own line, it is a little bigger so you can see it a little easier. So I want to graph, this is just a constant, times the exponential function evaluated at negative x minus mu all squared over 2 sigma squared. So it's easy to write it this way instead of putting all of this in an exponent. So exp of, say, z equals e to the z. That's just another way to write e to the z. But when we have a bunch of stuff up in an exponent, it's really small. It's hard to read, hard to keep track of what's going on. So sometimes we'll write the function this way. Okay, so let's give this a name. Let's call it f of x. And again, it has these parameters, mu and sigma. Sometimes we write this as f of x with a semicolon, mu and sigma, kind of indicating that these are parameters. These would be kind of fixed but arbitrary numbers, and x is the variable. But, in some sense, mu and sigma kind of operate like variables. They operate like unknown quantities. And that's actually going to be kind of our interest here is we're thinking if I changed mu, how would that change my graph, right? This up here would be kind of like the special case, more or less, where mu is 0 and sigma is 1, where I would get e to the negative x squared. That's more or less what I have here, right? I'm missing this like over 2, and I'm missing this correction constant out front, but that's more or less like what the previous example was kind of like a special case where mu is 0, sigma is 1. If any of you have taken probability and stats before, you might recognize this as the normal distribution, and you might recognize this function as being pretty close to the standard normal distribution with a mean of 0, standard deviation of 1. So that's a little aside, just the context for this problem. But how does changing mu and changing sigma impact the graph? That's what we're trying to kind of look at here. Okay, so first let's look for intercepts. Well, I kind of know, I can find a y-intercept, when x equals 0, y equals, I could plug in x equals 0, but it's going to be a mess. I could look for symmetry. But I don't really have, it's not a nice even function or an odd function or doesn't have nice translational symmetry. But something that I might notice is that I had nice symmetry in the previous problem. Why did I lose my symmetry here for this problem that's pretty similar? I'm not symmetric about y equals 0. Or I'm sorry, I'm not symmetric about the y-axis about x equals 0. But I am kind of symmetric about the axis x equals mu. So I do have a nice mirror symmetry, but it's about x equals mu. Right, if I let z be, say, x minus mu, I'd have like e to the minus z squared over 2 sigma squared. This would be f of z, and z would be the function expressed as z would be an even function. So I do have nice kind of even like symmetry about a different axis, x equals mu. I could evaluate this at mu. So f whenever x equals mu is going to be 1 over sigma root 2 pi. And when x is mu, I get mu minus mu squared is 0. I get either 0 or 1. So I just get 1 over sigma root 2 pi. By the way, mu and sigma are parameters. Pi is the number related to circles, like about 3.14. It's the good old pi that we always work with. Okay, so that's kind of nice, right? I didn't have kind of an easy symmetry here, but I had a little bit more involved symmetry. I had an axis of symmetry that wasn't the y-axis, that wasn't x equals 0. So if we look at vertical asymptotes or end behavior, no vertical asymptotes. But then again, if we look at f plus or minus infinity, that's going to be 0. If I let x get large positive or large negative, x minus mu is still going to be large positive or large negative, whichever one it was. I square that, put in the so e to the minus stuff is like, just to be really clear what I'm saying here, right? E to the minus stuff is like e to the plus stuff in the denominator. So if I make x very large or very large negative, x minus mu will also be very large or very large negative. I can square that, divide by 2 sigma squared, still very large positive or very large negative. E to that power is going to be very large positive now. But I think I said something wrong there. X minus mu, very large positive or very large negative. When I square it, it's very large positive. Divide by 2 sigma squared, still very large positive. E to a very large positive power, still very large positive. 1 over that goes to 0. So f at plus or minus infinity is 0. In other words, we still have a horizontal asymptote y equals 0 at either side. Okay, third, let's look for intervals of increase or decrease. Let me bring my function down here. I'll just copy it down. And I guess this is 3 and 4. So let's try to find f prime of x. So it has this constant 1 over sigma root 2 pi. And then I differentiate the exponential function. So derivative of e to the stuff is e to the stuff times the derivative of that stuff. And d by dx of this gives me a negative 1 over 2 sigma squared times 2 times x minus mu to the first, and then just times 1 if we want to throw in another chain rule. So we can ask, when is this 0? E to the stuff is positive. This stuff is negative. I guess all of this stuff, even including the 2, is negative. So the only thing that can be 0 is x minus mu. It's 0 whenever x equals mu. So I have one critical number, x equals mu. If I go to the right of mu, if x is bigger than mu, then what do I have? This 1 over sigma root 2 pi times negative 1 over 2 sigma squared times 2, that's negative. If x is bigger than mu, x minus mu is positive, and the exponential bit is always positive. So this is the only one that changes whenever x changes. But if x is bigger than mu, I have a negative number. And if x is less than mu, well, we kind of see that we have like an even function about x equals mu. So the derivative should be like an odd function about x equals mu. So we'd probably guess that we should have positive over here. And we can see that we get negative times, if x is less than mu, x minus mu is less than 0. Negative. And then the exponential is always positive. Negative times positive is positive. So we see f is increasing on negative infinity up to mu, and it's decreasing from mu to infinity. And we see we have a critical point at mu. We're increasing into it, decreasing out of it. So we have a local max at x equals mu. Any questions so far? And then let's look at 5 with the second derivative. Let me clean up f prime really quickly. Okay, so this 2 and that 2 can divide out. So I have negative 1 over sigma cubed root 2 pi times x minus mu, and then times the exponential. All right, let's just give this a name. We'll just call this maybe k, so we don't have to keep writing it. What's our second derivative then? It's going to be k times a bunch of stuff. Or well, let's think of it as k times x minus mu. Maybe that'll be a better way to think about it. So it's like kx minus k mu. The derivative of the first then is just going to be k. So k times x minus u differentiates to k times the exponential. I'm not going to write all the insides. The insides of the exponential all stay the same. Plus the first is k x minus mu times the derivative of the exponential. And its derivative is that. Let me get rid of this little dot here. So differentiate e to the stuff is e to the stuff times the derivative of the stuff inside, which is what, negative 2 x minus mu, or that's negative 1 over sigma squared times x minus mu. So we end up with k times the exponential that can come out times 1 from this first term, and then minus 1 over sigma squared times x minus mu squared. And our question is, when is this 0? Well, I know k is not 0. K is a negative constant. Here, sigma has to be bigger than 0. It's a little aside. But k is a non-zero constant. The exponential function is not 0. So the only way this can be 0, the only possible inflection points I have is when this bracket is 0. Or when x minus mu over sigma squared equals 1. or when x minus mu equals plus or minus sigma, or when x is mu plus or minus sigma. So we know that mu is an important point on the x-axis. It's the axis of symmetry. It's the location of the local max. And our inflection points are sigma units above and below mu. So putting this all together, what do I have? I have like a x equals mu axis. And instead of an x equals 0, instead of a y-axis, I'll write everything in relation to an x equals mu vertical axis. I see I have some positive output there. It's not a super nice positive output, but we're symmetric about x equals mu. So we want to look like an even function about this axis. We also know that f is always positive, and we have horizontal asymptotes of y equals 0. It's my x-axis at plus or minus infinity. Similar end behavior as we saw before. I see that f is decreasing up to mu and then, or sorry, increasing up to mu and then decreasing out of there with a local max at mu. So I do have something like this. I don't have any other changes in increase or decrease, so I do have this kind of tailing off to the sides situation here. Should look a little more symmetric than that, but as I always say, I'm not the greatest artist. And then I see that I have inflection points changing concavity. Pretty clearly, this is going to change from concave up to down to up at these points. Mu plus sigma and mu minus sigma. These points that are sigma units away from that axis of symmetry, mu. And let's actually put in the height here. I guess I was being lazy and didn't want to do that, but it's 1 over sigma root 2 pi. So what I can see is that mu is a location parameter. The only kind of anchor points for mu are where for the x location. If I increase mu, I just take the whole graph and shift it to the right. If I decrease mu, it takes the whole graph and shifts it to the left. Doesn't change the shape of the graph or what it looks like. It just shifts it along the x-axis. If I change sigma, my inflection points, say if I increase sigma, my inflection points will spread out. But also if I increase sigma, my peak will get shorter. So I'll get a wider, shorter, flatter curve. And if I decrease sigma, things will tighten into the center point mu. My inflection points will come in towards x equals mu. And if I make sigma smaller, it's on the denominator of this maximum output. If I make the denominator smaller, the whole fraction gets bigger. So this peak will get peakier. So for smaller sigmas, it'll look a little more like this. And for larger sigmas, look something more like that. So this green is sigma large, and blue is sigma small. And again, the kind of context in probability and stats is this is what's called the normal distribution or the Gaussian distribution or the bell curve. Mu is the mean, the kind of the average basically. So if we want to use this to model heights, we'd be talking about the average height. And that's where the peak is. And then sigma is the standard deviation, kind of how variable can things get? How spread out does the data tend to be? If it tends to be really spread out with a large standard deviation with a large sigma, the distribution will be wide and flat, meaning that you're kind of likely to find people in a pretty wide range or wide variety of heights. Where if sigma was small, if the standard deviation was small, most of your data is clustered around the mean, around the average. So if you pick somebody at random from the population, they're probably going to be close to average height, not really far away. So we can tell an awful lot about the impact that mu and sigma have on this graph, on this probability distribution, if you want to think of it that way. And we never even really wrote down a number, right? We didn't go through and pick different values for mu and sigma. This isn't something we could have done with a calculator. This is something that we pretty much had to work through by hand and understand how mu and sigma impact this graph and how changing mu or sigma is going to change the graph. So that's something that we understand now qualitatively about this model that we wouldn't have understood before. So I think that's really the crux of, why are we doing this? It's less for things like graphing this, right? These are kind of like warm-up problems or just practice problems. It's more for problems like this one here. Now, we tend to do a few more of the previous type of problem because they're a little more closed-ended, a little easier to do. The calculations are a little more straightforward, but this is kind of the end goal, I think, of this section. And we see models like this all the time that have parameters. And the reason is that if I go through the trouble of developing a model, if I were to only use, if I were to say this is the normal distribution, how many things are symmetric about zero, right? How many things have that like standard deviation or whatever you want to call it of, say, exactly one? Not very many. If I try to apply this function just as it is as a model to, people's heights in Pittsburgh, it's probably going to be a pretty terrible model. I want to have parameters in my model like the mu and sigma here, or like different parameters in another model that allow me to tune that model to the data set that I'm working with. So I can choose a mu, a kind of center point that's maybe around 5'7" tall, 5'8" tall, something like that, whatever we think that the kind of typical height is for people in Pittsburgh. And I might choose a standard deviation that I think matches what I expect to see from the heights, maybe say 2 inches or 4 inches, something like that. Any questions on any of this so far? So something like this is much more abstract. It's a little harder to grasp, but I think it's also much more valuable. But because it's more abstract, more difficult to grasp, that's why we do fewer examples like this and more like this one here. Let me get a little more room here. So a couple more examples. We have an example that's more of a closed-ended, one that's a little more open-ended, and then one kind of capstone one that's, again, a little more closed-ended. Okay, so let's graph x squared log x on the domain x bigger than 0. So we will let f of x equals x squared log x. And again, just like usual, the first thing we'll do is we'll look at intercepts. Well, here my domain x bigger than 0, there is no y-intercept. So in fact, I'm only in quadrants, so not 2, quadrants 1 and 4. Do I have an x-intercept? If f of x is 0, what does x have to be? Well, I mean, I suppose if we look at the x squared factor in isolation, we could zero things out by choosing x equals 0, but that doesn't comply with our domain restriction or with the natural domain restriction of log. So, we might think x equals 0, but that's not really an x-intercept. The other possibility is log x equals 0. And if log x is 0, that means x equals 1. Right? Log of 1 is 0 because e to the 0 is 1. So x equals 1 says that y is 0. 1 comma 0 is our one and only x-intercept. Two, let's look for asymptotes in end behavior. Are there any vertical asymptotes? Well, there's a part of me that looks at that log x and I say, well, I mean, I know that if I just had f of x equals log x, I would have a vertical asymptote at x equals 0. So I'm a little suspicious about this. What about x equals 0? Does that give me a vertical asymptote? I do have an x squared log x now, so I'm not really 100% sure. If I look at end behavior, horizontal asymptotes or end behavior, and behavior, there we go. I kind of have two ends. I have a plus infinity, f at infinity. Well, if I put a big positive number into x squared, I get a big positive number out. Big positive into log x, I get a big positive out. Multiply the two together. Okay, well, we shoot off up and to the right. So that was easy enough. My other kind of end is actually like x equals 0. Now I can't plug in x equals 0. I would get like something like 0 times negative infinity. But I want to investigate this, right? I'm not really sure what's happening at x equals 0. Kind of feels a little bit like a vertical asymptote, kind of feels a little bit like an x-intercept, like a root. Kind of feels like I should go through 0, 0. Kind of feels like an indeterminate form. Let's take a closer look at this. So limit x goes to 0 from above of x squared log x. I notice that this is kind of like a 0 times infinity indeterminate form. We've seen these types of limits before in L'Hopital's rule. So if I change this x squared into a 1 over x squared, well, log x as x goes to 0 from above looks like an infinity. 1 over x squared as x goes to 0 from above also looks like infinity. I now have an infinity over infinity type limit, type in an indeterminate form. I can L'Hopital this. I differentiate the numerator log x to get a 1 over x. I differentiate the denominator 1 over x squared. That's an x to the minus 2, giving me minus 2x to the minus 3. I can flip that denominator and bring it up top. So I got a 1 over x divided by negative 2 over x cubed. So I got 3 factors of x coming up top. One of them cancels. I get an x squared over negative 2 when everything is settled. And here I just have a rational expression or a polynomial, however you want to look at it, with no domain issues. I can just evaluate this. This is 0. So I don't really have a vertical asymptote. No vertical asymptote. That kind of x squared factor stepped in to save the day and keep us from shooting off to plus or minus infinity at 0. And I kind of have end behavior. I kind of like, kind of an x-intercept of 0, 0. But this isn't actually a point on the curve. It's just an open dot where we approach. So I'm putting it in quotes, you know, open dot. I'll make myself a little note there. So when I draw this picture, I'm going to have something at 0, 0, but it's not going to be a point like that. It's going to be an open dot. I also have an x-intercept of 1, 0. That's a legitimate intercept. That's 1, 0. And I know I have to shoot off this way. Do I do something like this? Right? Do I do like come down and just touch and then go, I have a couple anchor points. I know a little bit about the end behavior, but not really sure what happens in between. Let's look at the first derivative. So f of x is x squared log x. F prime then is 2x log x, differentiating the first, plus x squared times 1 over x, differentiating the second. So that's 2x log x plus x, or f prime is x times 2 log x plus 1. I want to know, when is this 0? Well, that's whenever x equals 0. How can I put that in quotes? Because while x equals 0 isn't really in our domain. But I do kind of see that if I were to take the limit as x goes to 0 of f prime of x, I see that this is going to go to 0 as x goes to 0, right? That x log x from the first term, the x kind of beats the log x. We could L'Hopital improve that, and of course the plus x term just goes to 0, obviously. So it seems like we have a horizontal tangent at 0, so it doesn't seem like we're going to go like this. We might do something like that. We might kind of come out straight and then dip down, or come out straight and then go up, and a couple of different options. But we got a little bit more clarification from there, maybe. And then the other possibility is that log x equals -1/2, or x is e to the -1/2. That's 1 over something to the 1/2 power is just square root of that thing. 1 over root e. So I'm going to write my interval like this. Here's 0. And here is 1 over square root of e. This is the form of f prime that I'm going to use to evaluate this, because it's a nice product of two functions. I know this first factor is always going to be positive, because our domain restriction is x bigger than 0. So the sign of f prime, plus or minus, is just going to be the sign of this 2 log x plus 1 factor. Okay, so 1 over square root of e. Well, that's 1 over a number bigger than 1. That's a number less than 1, so I could pick x equals 1 as a test point. F prime of 1 is going to be a positive, times, well, log of 1 is 0. So I get 2 times 0 is 0, plus 1 is positive. So f prime is positive from 1 over root e L to infinity. That meshes with what we saw with our end behavior as well. How do we shoot off to positive infinity if we didn't have a positive derivative? So that meshes with what we saw before. What about from 0 to 1 over root e? It's tempting to pick a number like, 0.1 or something like that in here, because that seems like a nice number. But remember, the goal is to plug into the log. So I want to pick something that when I log it is going to be nice when I take the natural log. I mean, 1 over square root of e, well, I guess 1 over e, right? E is bigger than square root of e, so 1 over e is less than 1 over square root of e. And when I plug this in, 1 over e is just e to the negative 1. It's going to log very nicely. So f prime of e to the negative 1, which is in this interval from 0 to 1 over root e. Well, I have my first factor x, but of course that's positive. 1 over e is a positive number. And my second factor, 2 times log of e to the minus 1, that's 2 times minus 1, right? Log of e to the minus 1 gives me minus 1. So negative 2 plus 1 is negative. Negative. So my first derivative on this left-hand interval is negative. Okay, so I'm decreasing on 0 to 1 over root e. And then increasing on 1 over root e to infinity. And I have a local minimum at 1 over root e. And let's actually figure out what the output of that is. That's an at sign, poorly drawn at sign. So local minimum at x equals 1 over root e, and what will be the associated y value that we're going to do f of 1 over root e. So f is x squared log x. Or that is negative. This is just negative 1 e to the minus 2, or 1 over e squared. Okay, so this is 1 here. 1 over root e is somewhere between 0 and 1. I see I have, what was it? Was it negative 1 over e squared? So that's like, I mean, e squared is like roughly 3 squared or 9. So that's like negative 0.1, something like that. Negative 1 over e squared. So we're kind of coming out this way, coming down, and then looks like we're increasing out of there. There's one little nuance that I'm not really sure about, and that's whether I have some behavior over here that looks more like, say, root x or log x, where I'm concave down. I'm kind of still heading off to infinity, but going sublinearly, going like slower than a linear function, or whether I am concave up, where I look like x squared or e to the x or something like that, where I'm going to infinity superlinearly. Sometimes this is actually quite important. You look at a lot of algorithms in computer science and programming and so on. They're very concerned about, are you sublinear, or does your problem, your computational time scale like log x? Does it scale logarithmically? Does it scale linearly like x? Does it scale superlinearly like x log x, or even worse, like x squared, or exponentially like e to the x? They're quite concerned with this end behavior. Let's see if we can get an idea of whether we stay concave down or whether we're concave up, shooting off to infinity over here. We expect to be concave up at least for a little while, around 1 over root e, and it kind of feels like we should be concave down for a little while, kind of coming out of, it seems like we have a horizontal tangent and then we start diving down. So it seems like concave down, concave up. Do we switch concavity again? Do we keep concave up? Let's check. This isn't going to be too bad to take the derivative of, so let's go ahead and do it. So problem 5, or not problem, part 5, second derivatives. Instead of using the factored form, which is harder to differentiate, I'll use the initial form, this 2x log x plus x. And we'll take the derivative. So I differentiate the first, I get a 2 log x, plus I keep the first, differentiate the second, 2x over x is just a 2. Differentiate the next term, just differentiates to 1. So 2 log x plus 3. Then I want to know, when is this 0? That's when log x is negative 3 over 2, or when x equals e to the negative 3 halves, or what is that, 1 over the square root of e cubed, if we untangle all of those bits and pieces in the exponent. Just like the function of first derivative, the second derivative is only valid for x bigger than 0. And I see I have this potential inflection point 1 over root e cubed. F double prime is actually pretty simple. If I pick a test point, say between, and this is 0, 0. If I pick a test point between 0 and 1 over root e cubed, say 1 over square root of e to the fourth, or 1 over e squared, or e to the minus 2, should do the trick. Right, this is 1 over root e cubed is like 1 over e to the 3 halves. So changing that e to the 3 halves to an e to the second power puts more in the denominator, making the whole thing closer to 0. Or say if I put less in the denominator, if I put, like, instead of 3 halves powers of e in the denominator, if I put 2 halves powers of e, say like 1 over e, that should make the whole thing bigger. So e to the minus 1 might be a nice test value to the right of 1 over root e cubed. So these are my two test values. Again, I picked them because I know that I'm going to have to log them. I'm picking things that are easy to log. I definitely want to pick these if I wasn't plugging them into a log. I would pick nicer numbers like 1/2 or 1/10 or something like that if I wasn't going to log them. But I see that e to the negative 2, log of e to the negative 2 is negative 2, times 2 is negative 4, plus 3 is negative. And e to the negative 1, plugging that in, log of e to the negative 1 is negative 1, times 2 is negative 2, plus 3 is positive. Right. If I set myself up pretty nicely, actually doing the figuring out of the intervals isn't too bad. It's the preparation and setup that takes a while. So I see that I'm concave down on 0 to e to the minus 3 halves, e to the minus 3 halves. And I'm concave up on e to the minus 3 halves to infinity. I have an inflection point at e to the minus 3 halves. But importantly, I look more like, where did my picture go? Is it? Oh, it's all the way back up here. More importantly, I look like this rather than that. I stay concave up to the right. So I something more like that. See if I can clean this up just a touch. There we go. So I have my inflection point here. This is 1 over root e. And somewhere down here, I have 1 over root e cubed, where I have the inflection point where I go from being concave down to concave up. And if I wanted to, I suppose I could zoom in a little bit and try to draw that a little nicer in there, but I think we can use a bit of artistic license here and say that I think this is good enough. We've got all the important features, the local min, the fact that we come out of 0, 0, not really come out, but we start out of 0, 0 kind of with a horizontal tangent, go down, reach our local min. Somewhere in that interval, we become concave up, and then we stay concave up from there on out. going through the point 1 comma 0, our x-intercept. Any questions on that? All right, so let's take a look at this next problem. Here we have the relativistic energy equation. In relativity, the energy in special relativity, the energy of a particle is given by E of lambda is root m naught squared c to the fourth plus h squared c squared over lambda squared for lambda bigger than 0. What does all this mean? Well, m naught is the rest mass. So this would be like if there was an object that you're interested in, a particle you're interested in, it's sitting in the same frame you're in. So it's like sitting there and it's not moving relative to you. You measure its mass in that situation, you get an answer. That's its rest mass. Now, once it starts moving, special relativity says weird things happen with how you would measure mass and speed and all of these kind of things. So h is Planck's constant. It's some positive number. That's all we really need to know. It's a really, really small number, something like 10 to the minus 34. It's a really, really small number. C is the speed of light. It's a number greater than 0, really, really big number. Something like 10 to the, 8th or 10 to the 6th or something like that, depending on what unit you're using. So we have really small number squared times really big number squared makes, it probably nets out to a pretty small number squared still, but. And then we have lambda coming into play as well, the wavelength of the particle. So we can think of this like maybe a photon, like a particle of light, but we could also actually think of this as kind of a different particle also. If we think of it as a non-photon, it might have some positive rest mass. So my energy is really, my energy function here, I mean, C and H are just numbers. They're universal constants. They are what they are. They're not going to change if you look at a different particle or in a different situation. That C and H are numbers. You could plug in the numbers, 3 and 5 for them or something, and you would get qualitatively the same outcome. Don't do that. Don't tell the physics professors that I said to plug 3 and 5 in for H and C, but my point is the picture would look the same. But what we're interested in is, well, we're thinking of the energy as a function of wavelength. So this particle can have a different wavelength that can maybe be excited or more energetic or something and have a different wavelength. But how does that energy of the particle, how is it dependent on the parameter rest mass? That if I was looking at a different particle, it would have a wavelength energy spectrum that would be a little different because it has a different rest mass. What does that rest mass do? So that's what we're trying to evaluate here. So again, we could plug in numbers for C and H, but we wouldn't be able to plug the energy function into a calculator because energy is our dependent variable, lambda is our independent variable, but we have this parameter m naught parameterizing a family of functions. What does m naught do? If I increase or decrease m naught, what effect does it have on the graph? We're kind of asking a similar question to up here, where I asked like, well, if I change mu, what effect does mu have on the graph if I change it? So it's kind of a similar question to this one down here. All right, let's get started. So first, let's look for symmetry. We kind of like feel like we want to say it's an even function because we see the lambda squared, but the problem is lambda is bigger than 0. So we don't really want to say it's an even function. It's not going to be symmetric about the y-axis because we can't plug in negative lambdas to start with, right? A negative length of something doesn't seem like a very reasonable physical measurement. Do we have any intercepts? What about E of 0? I mean, if I try to plug in lambda equals 0, that's no good. What about E equals 0? Well, if I want E to be 0, I actually see that E is always going to be positive, right? It's a non-negative thing, and I should say rest mass bigger than or equal to 0. It's a non-negative thing plus something that is strictly positive under the square root. So it's always going to be positive. I mean, I guess I got one thing out of here. E of lambda is positive. We're always going to be in quadrant 1. We won't have any parts of our graph in quadrants 2, 3, or 4. So, I mean, I guess that's a plus, but I didn't get much else out of part 1. Part 2, what about horizontal asymptotes and behavior or vertical asymptotes? Well, vertical asymptotes, we did see that as lambda goes to 0, we might have a little bit of an issue. So sometimes this is labeled something like E at 0 plus, or meaning limit lambda goes to 0 from above, E of lambda. Well, as lambda goes to 0 from above, this term goes to positive infinity because this is always a positive term and the denominator is getting smaller. So this goes to positive infinity. If I add on a constant, still goes to positive infinity. If I square root something going to positive infinity, still goes to positive infinity, right? Just using my limit laws, pushing the limit all the way inside there till I get limit of 1 over lambda squared as lambda goes to 0 from above. And that's plus infinity. I actually have a vertical asymptote at lambda equals 0. I'm probably going to at some point call it x equals 0 or x equals whatever, but I'll try to remember to call the independent variable lambda. Variable vertical asymptote at lambda equals 0, vertical asymptote of plus infinity. So I know that I'm doing something like this. What about a horizontal asymptote? Well, I can't go to negative infinity because lambda's positive. But as lambda goes to plus infinity, let me just copy this down. I see that as lambda goes to plus infinity, this term just drops off. I get root m naught squared c to the 4th. Hey, that's E equals m naught c squared. That seems like a famous equation. So I have a horizontal asymptote um, E equals m naught c squared at lambda equals infinity. So the famous E equals mc squared, that's really a special case of this more general energy formula when we have an infinite wavelength or zero frequency, or when our particle has kind of basically no kinetic energy, so to speak, and only this kind of potential energy. So we have a horizontal asymptote of E equals m naught c squared as well. We know that's a positive number, but I'm not sure, does it come down and come back up to there? Does it come down to there nicely like that? Does it come down and, wiggle around or something? What happens? How do we approach this asymptote? I'm not really sure. We know that we do something like that as we go way off to the right, but again, we kind of know some stuff about some anchor points, but it's those in-between values that, number one, are quite interesting, where we might have interesting behavior, but number two, we don't have a lot of information about from just the algebra and the pre-calc. So third and I guess fourth, let's look at the first derivative. So E prime of lambda. Well, I'm going to rewrite this. Can I bump that down one while that running? Okay, good. I'm going to rewrite this as stuff to the 1/2 power. And actually, I'll even do this. Let me clean this up just a little bit. I want over lambda squared to be lambda to the -2, and this all to the 1/2 power. Oh, I lost part of my plus sign there. There we go. I think this will just help us differentiate it a little more easily. So I have stuff to the 1/2, that differentiates the 1/2 stuff. To the negative 1/2 times the derivative of the stuff inside with respect to lambda. That's a constant with respect to lambda, that differentiates to 0. This stuff differentiates to h squared c squared times -2 lambda to the -3. And I think we're good. This 1/2 divides out with that -2. And I have e prime of lambda is, well, e is square root of this stuff, right? So it's like over e. I guess I can just write it that way. And I have negative h squared c squared uh, e times lambda cubed. Well, h squared, c squared, lambda cubed are all positive. We said before that e is positive. E of lambda is always positive. So this stuff is a whole bunch of positive stuff multiplied by a -1. The derivative is negative everywhere. There are no critical numbers. There are no points of non-differentiability. There are no local maxes or mins. So in some sense, this is kind of a boring function, but we've confirmed that. We confirmed that it just comes down and does this. What effect does M naught have? M naught sets that bottom point. It sets that horizontal asymptote that we're approaching from above. If M naught was a little higher, we would be approaching a value that's a little higher, or if it was a little lower, we'd be approaching that instead. So this is what our graph of E as a function of lambda looks like. Shoots off to plus infinity as lambda heads to 0. As we get shorter wavelength, we get higher frequency. That's a more energetic particle. And as our wavelength goes to infinity, as we get a lower frequency, we have a particle with less kinetic energy and almost all of its energy than its potential energy. So that's kind of the floor. We have the potential energy of the particle acting as the floor, and then the kinetic being kind of added on top of that. But all being additive under this square root deal. Any questions on any of this? Okay, and in the last, what do we have, 20, 25 minutes or so, let's work through this last problem in graphing. We should be able to get through graphing today, so that's nice. Kind of a pretty big section. Let's work through this problem. Graph x over log x for positive x's. This kind of looks pretty similar to x times log x, but the log x is in the bottom, so we're going to have to be a little bit more careful about things. Okay, let's start with our basic algebra stuff. Of course, we're not looking for symmetries here. There's obviously no translational symmetry, and evenness or oddness is blown out of the water because we have the domain restriction x bigger than 0. What about intercepts? So let's call this f of x equals x over log x. What about a y-intercept, f of 0? Well, f of 0 is like, it's kind of like 0 over infinity. Maybe we'll treat this in the next, in part 2, maybe we'll treat this as a limit. So We'll think about that as a limit, as kind of an end behavior issue. So f of x equals 0. Well, the only real way to get f of x equals 0 is to plug in, or to have the numerator be 0, which means plugging in a 0 for x. But then I'd be in the same situation as up here. So that's not super helpful either. Not really, not a whole lot of help finding any intercepts, x or y intercepts. I feel like there was something else that I missed. Oh yeah, just general points of interest. One thing that I might notice is that, like, say f of e, that might be kind of easy to compute. Log of e is 1. The f of e is actually e. That's kind of interesting. Right. That's maybe like an anchor point that might be helpful in the future. The only reason I came across that was it made the denominator look nice. Right. I mean, f of e squared is, well, log of e squared is 2. That's like e squared over 2. Is that going to be helpful? Like, I'm not sure. If I needed another point here or there to help me out, I kind of see that, like, f of e to the n is going to be kind of helpful. It's going to be like e to the n over n. So, maybe I'll keep that in mind. If I want a little bit more granularity later on, if I want a couple extra points to help me out with something. Might help, might not. Okay, second, let's look at asymptotes. So look at vertical asymptote or end behavior. What happens to limit x goes to 0 from above f of x? Well, as x heads to 0 from above, I get a numerator that gets closer and closer to 0, and a denominator that gets closer and closer to negative infinity. Well, this whole thing is going to 0. So I might be able to say something like f of 0 from above equals 0. So again, kind of like the last log problem, we have this kind of point 0, 0, but it's like an open dot. So we have a point like 0, 0, but we want to make sure that we put an open dot there, not a closed point. So we're going to have something like this. We don't have anything in quadrants 2 or 3 because x has to be positive. What happens as x goes to infinity? Our horizontal asymptote or end behavior, f at infinity, well, we have an infinity over infinity type limit, right? This is L'Hopitalable. So I have what? 1 over x. The x flips up top. So my end behavior is I shoot off to positive infinity on the right. So I got a little bit out of computing my limits. One kind of anchor point at 0, 0-ish, and I know that I'm shooting off to positive infinity as x goes to positive infinity. Still don't know a whole lot about this function. Let's look at its first derivative. There we go. Okay, so f of x is, let's see, do I want to use quotient rule here? I might as well. It's not that bad for this one. log x squared. I have bottom derivative of top, which is just log x, minus top derivative of bottom, or my derivative f prime is what, log x minus 1 over log x squared. So here I want to look for critical numbers, and here I actually have 2 points of interest. When can it be 0? But it could also maybe not exist. So if x equals 1, in the numerator I have log of 1 is 0, minus 1 is negative 1. But in the denominator I have log of 1 is 0. So x equals 1 could be problematic. I actually probably should have pointed that out up here too. I forgot to point out this domain issue that f doesn't exist at 1. Right. So f doesn't exist at 1, the derivative doesn't exist either. If I plug in x equals 1, I get 1 over log of 1, 1 over 0. So x equals 1 is a critical point because the derivative doesn't exist there. F prime is 0. Well, that's when log x minus 1 equals 0, when log x equals 1, or when x equals e. Right, log of e is 1, minus 1 gives me 0. And on the bottom, I have log of e squared. That's just 1 squared on the bottom, so nothing blows up or nothing is problematic in the bottom. So I have 2 critical points, 1 in e. And I want to evaluate f prime at a test point in each of these intervals. Maybe I'll choose like e to the minus 1. I know I'm going to be plugging into lots of logs, so I'll pick something easy. E to the minus 1 for here. Maybe something like square root of e. So 1 over e is between 0 and 1. Say like square root of e, e to the 1/2 is between 1 and e. And maybe something like e squared is an easy number that's bigger than e. So what is f prime of e to the minus 1? So I see in my denominator, I have a positive because it's something squared. Log of e to the minus 1 gives me minus 1. Subtract 1 again, that's minus 2. That is negative. So my derivative is negative between 0 and 1. What about the test point e to the positive 1/2? Square root of e. Well, again, my denominator, log of e to the 1/2 squared, that's going to be positive. My numerator, log of e to the 1/2 is 1/2. 1/2 minus 1 is negative. Or negative here as well. And then e squared. Well, again, log of e squared in the denominator is 2. 2 squared is 4. That's going to be positive. Log of e squared is 2. Minus 1 in the numerator is positive. We kind of expected that because remember, our end behavior is we have to shoot up and to the right. So eventually we have to have a derivative that turns positive. But it's negative from 0 to 1 and negative from 1 to e, and then positive after e. So we're decreasing on 0 to 1 union 1 to e. We're not differentiable at 1. Our function doesn't even exist at 1. So we have to be careful not to just lump this all together and say the full interval 1 to e, or sorry, full interval 0 to e. We have to go 0 to 1 union 1 to e. And we're increasing on e to infinity. I do note that I am differentiable at e. I decrease into e, I increase out of e. So it looks like I have a local min at an input of e. And we noticed before that that's actually associated with an output of e. So that happened to be our local min. That was a nice number to evaluate. Um, and I realized that when I came across this and forgot to mention that x equals 1 is a point where f is undefined, we probably should evaluate that and look at what happens as x goes to 1. Okay, as x goes to 1 from below, and as x goes to 1 from above. So at 1 here, we're undefined. But what happens as we head to 1? And f is x over log x. So as the numerator heads to 1 from either direction, the numerator is positive. As x heads to 1 in the denominator, well, what does log x look like? This is the graph of just log x. There is 1 comma 0. And so I see as we approach 1 from below, log x is going to be negative. Versus as we approach from above, it's going to be positive. In both cases, I'm going to something like 1 over 0, but I'm going to have like 1 over a small negative number, which is going to be a large negative number, versus 1 over a small positive number, which is a large positive number. So we have a vertical asymptote here. We're going to be heading down to negative infinity when we're approaching from the left, and coming down from positive infinity as we pass over and are just to the right of it. So sorry that I skipped over that detail. I knew there was something else I wanted to say up here, and I thought it was the points of interest, but it was actually this piece there. Okay. So we now see that we're decreasing on 0 to 1, union 1 to e. That actually makes sense. We're kind of decreasing down here. We jump over the vertical axis and we're decreasing. And then we hit a local min at e comma e, and then we start increasing. And now I still have a question. Am I going to do something like that or something like that? Do I change concavity? Do I keep the same concavity? Pretty clearly, we're going to be kind of concave up here around x equals e. But do I change concavity? Do I keep the same concavity? Okay, so f prime is what? Log x minus 1 over log x squared. I think this is probably about my limit for computing a second derivative or calling it too much work. But if we really wanted to know concavity, we would need to do it, even if it was a lot of work. Right, so we have over the bottom squared. And then we have bottom derivative of top. So bottom log x squared. Yeah, bottom derivative of top is just 1 over x minus top. Derivative of bottom is 2 log x times 1 over x. I think we can simplify a couple of bits here. I can pull out a 1 over x times log x from everything on the top. And move this equal sign to a more reasonable place. So I pulled out a 1 over x log x from everything. So I'm left with log x minus log x minus 1 times 2 over log x to the fourth. Can do a little more work here. And so here I have over x log x cubed. That takes care of the factor in front of the 1 over x and the factor of the log x on the top that divides out with one of the log x's on the bottom. And here I have a log x minus 2 log x's, so that's minus log x. And then I have minus a minus 1, so plus 1 times 2. So I think I'm going to check my algebra here really quickly, but that should be what I end up with. Let's double check. Yeah, that is looking good. Okay. So I think that's about as nice as f double prime is going to get. So not too bad, all things considered. I want to know, when is f prime equal 0 and when does it not exist? Well, it's not going to exist whenever x is 1. And it's going to be 0 whenever log x equals 2 or when x equals e squared. So my picture for f double prime looks like 1 and e squared for f double prime. And let me pick some test points. The difficult thing to plug into is going to be the logs. So I'll use something like e to the minus 1 here. 1 over e is between 0 and 1. This is 0 on the left here. OneNote is starting to lag. I wrote too much on here, I guess. And then between 1 and e squared, I mean, e would be a good one, e to the first power. And to the right of e squared, maybe e cubed for test points. So let's do f double prime of e to the minus 1. Log of e to the minus 1 is minus 1. 2 minus a minus 1 is plus. That's a positive. 1 over e is positive. Log of e to the minus 1 is negative 1 cubed is negative. So we should be negative or concave down, negative second derivative or concave down on 0 to 1. F double prime of e to the positive 1. Log of e to the 1 is 1. 2 minus 1 is positive. X is positive. Log of e to the 1 is 1. Cubed is positive. We should be concave up here. Do we change concavity? Let's see. 2 minus 3 is negative. E cubed is positive. Log of e cubed is 3. Cubed is positive. We do change concavity back down. So we're concave up on 1 to e squared. Make sure to choose my black marks as the Endpoints on my intervals, and the blue ones are the test points. Concave down on 0 to 1 and on e squared to infinity. So we verified that we actually do have a change in concavity here at the end. We do switch to being concave down after e squared. So we basically look like this. We kind of come out from 0, 0, head down to this vertical asymptote, come down from above, hit our local min at e comma, whatever that was, e comma e. And then we change concavity at e squared. We have an inflection point, but we still go off to positive infinity, just more like a square root or a log than like, say, an x squared or an e to the x. So this is another reason that we might be interested in doing this. If we graph this on a calculator, we could just graph this. But the window that we choose, we might actually never see that it really changes concavity. It might be subtle enough on the window that we choose, or we might even choose a window that's a bit too small and never see that it changes the concave down. But we got all of our important information about um, intervals of increase and decrease and concavity. We got it all analytically, so we're not reliant on looking at the calculator to make those decisions. Any questions on any of this? All right, I will stop the recording then.